How can we group these things? Remember that these diagonal ones are not adjacent, so we really can't group those. But we can group this guy. And because wraparound adjacency, we can group this guy. These right here, can't do much about. Okay? So what is, I'm going to go ahead and let's do just this term, just that term. Those are easy because it's A or B or C or D. 0, 0, 0, 0. This guy is A, not B, C, not D. Now these two guys here. So let's do the one that goes up and down. It looks like A can be any value, but it's got to be a not B, and it's got to be a not C and a D. Because C is always taking the value of 1, and D is always taking the value of 0. And that's ANDed together. And now this guy that's going left to right with a wraparound adjacency, it looks like A and B always have to be a 1, so A or, excuse me, not A or B or not B. And then C is a 0 and a 1, so that doesn't matter. But D always has to be a 0. So our final answer should be basically the Boolean multiplication of all these sum terms and one second. So not B, not C, D, and then that final one, not A, or not B, or D. Pretty cool, huh? So now the sweetest thing about this whole Karnaugh map for POS expressions and SOP expressions, basically you can, we just did POS expressions. We can take this same Karnaugh map and just figure out what the SOP expression of that is. Sometimes the SOP is easier to implement, sometimes the POS is easier to implement. So let's take our first example, our 3-variable Karnaugh map here, and figure out what the SOP expression is. So let me go ahead and grab that, and we'll bring it down for a new workspace. And if we remember right, the expression for that POS was this guy right here. Oh, where'd it go? What's going on? There we go. So it's A or not B, ANDed with not A or C. So we want to see if the SOP expression is any easier to implement. Put our ones in there and just go ahead and start grouping those. So this one here is going to be what looks like A has to be a 1. B can be 1 or 0. And again, this is a product here. So it's C has to be a 1. And now what's this guy over here? It's the sum. And this is a product term in here. It looks like it's got to be not A. It's got to be not B. And C can take any value. So we can also implement this product of sum term right here as that SOP. You should be able to get the same results. Just, I mean, have we added anything? Excuse me, have we reduced the number of gates? Not exactly. This is going to be an AND gate for AC. It's going to be an AND gate for not A, not B. And those guys are going to be ORed together to give our value X. What is this one here? Product of sums. It's going to be an OR gate, A, not B. It's going to be an OR gate, not A or C. And those are going to be ANDed together to give us X. So POS, SOP. Just a pretty cool way. You can just do one Karnaugh map and come up with different implementations of the same logic expressions. Sometimes you gain something, in the form of smaller connections or smaller number of gates. So that's pretty cool about that. Okay, so we are not going to do 5-variable Karnaugh maps. If you want to, it's entirely all a 5-variable Karnaugh map is just you overlay. If you could think about it two-dimensionally, where in this one is a equals 0 and this one is a equals 1, you overlay two 4-variable ones, but we're not going to do that. We've got the basics for 3 and 4-variable Karnaugh maps. And we are going to talk a little bit about some SPLDs, and then we're going to finish up chapter 4.